In this lecture, I will show you how to compute the Jacobians. I'll give you an example of how to do it, and then I'll also show you very important change of variables from Cartesian to polar, Cartesian to cylindrical, and Cartesian to spherical. This is not a derivation. All it is the calculation of this change of variable. So first, here's an example of changing a double integral, having change of variable for a double integral. So we started here with our original formulation in terms of x and y, our original variables. Then we have a change of variable. Remember, write the old in terms of the new. So x equals, in this case, u plus v, and y equals 2v. Now, when I make the transformation, this is what was talked about in the previous lecture. I have to take the function, and I have to write it in terms of the new variables. That's what I've done here. F of u, v. Well, every place there's an x, of course, I write u plus v. And every place there's a v, I write y, I write 2v. So carry out that algebra, and all you get is a u. Now I have to compute the Jacobian. And to do that, I take the partial derivatives. So the partial derivative of x with respect to u is 1. The partial derivative of x with respect to v is 1. Now for the second row, I take the partial of y with respect to u, that's 0. And the partial of y with respect to v, that's 2. Taking the determinant, I get 2. That is the value for the Jacobian. So I have this done. I now have the Jacobian computed, and I can assemble the new problem right here. So I have the u because that's my function that I reevaluated. So the u goes right there. Then I have the Jacobian. I put that next, and then du dv. Just fill this in. Of course, the u can come outside, and now I'm just integrating double integral of u du dv. You would have to change limits as well, and that's pretty straightforward. Now I'm going to derive the Jacobian for polar coordinates. Not really derive it, just calculate it. These transformations from Cartesian to polar, Cartesian to cylindrical, and Cartesian to spherical are done and stored in the back of handbooks. For the homework, I want you to work out the details so you're familiar with how they're worked out. But they're so frequent, and it's so frequent, you know, that you would take cylindrical and turn it to, Cartesian to cylindrical or Cartesian to spherical, that these are just stored in the backs of handbooks. On tables of integrals are stored in the backs of handbooks for physics too. So here we're going to go to polar coordinates. So we're doing the same thing that we've talked about before. We're going to take an original formulation in terms of x, y. It's going to be Cartesian variables. That's my original formulation, and I want to change the variable. And to do that, I rewrite the function in terms of the new variable. I compute the Jacobian, and then I multiply or put in those operators du dv. So here's the transformation from the old to the new coordinates in terms of for polar coordinates. X equals r cosine theta and y equals r sine theta. So now I have to compute the Jacobian. So the Jacobian is that matrix of partial derivatives. Here I've written this transpose of it. So I can take x with respect to r, will give me cosine theta. Y with respect to r gives me sine theta. Second row, I did all my derivatives with respect to theta. So I get minus r sine theta for the partial of x with respect to theta. And then for the partial of y with respect to theta, get r cosine theta. Taking the determinant gives r cosine squared theta plus r sine squared theta. Of course, the r factors out, and you have the Pythagorean identity for sines and cosines, which is 1, and so the Jacobian is r. Remember, the first example it turned out to be 2. Here it turns out to be r. So here's how you write a transformation from Cartesian to polar. You take the function f of x, y, and you just write it in terms of r theta. The dx dy gets replaced by r dr d theta. You can memorize this if you want. It appears very frequently. So the Jacobian to go from Cartesian to polar is r. You never have to compute this again, well, if you remember it, except for homework, in which I want you to compute some of them. But that's the answer. It's r. just to show you how this works, let's compute the inside of the circle. So we have a circle, and we start in, let's look at what the variables look like in xy. So here's my circle. And now how do you find, I want the inside of the circle. This is, I'm sorry, y and x. Right. Remember how to find the variables? You pick one that's going to have the constant variables. This is a circle of radius r, so it's going from minus r in x to positive r in x. So I will put the, oh, this is wrong. No, this is right. Okay. Sorry, leave it like that. Okay, I have to have, one of the variables is going to have constant limits. In this case, I chose y. I could just as well have chosen the other. So I put that on the outside. So here's my y integration. It's going to proceed from minus r to plus r. To find the limits in the other direction, in the x direction, I draw a line parallel to the x-axis, and I find the curve where it enters the region and a curve over here where it leaves the region. Of course, the equation for the circle is x squared plus y squared equals r squared. So x is r squared minus y squared, and I'd be taking the square root, and of course I have plus and minus there. Right. So where it comes in, I'd be on this part of the circle. That's where I get the lower limit of integration. And when it leaves, over here, I'm on this section of the circle, and that's where I get the upper limit. Now, there are the equations, and you can integrate that if you wish. Everything's continuous. You could actually do it the other way as well. But it's much easier to go to polar coordinates. So here's, I put again always the kind of template here for what we're doing, and I'm going to go to polar coordinates, r and theta. So the f in terms of xy gets rewritten in terms of r and theta. And the dx dy gets replaced by the Jacobian times the du dv, which in this case is dr d theta. The Jacobian was r, so the whole thing that appears over here is r dr d theta. So dx becomes r dr d theta. In this case, the function is 1, so there won't be any change, right? So here was the original formulation here, and the dx dy are replaced by r dr d theta. So I carry out this integration. Notice what r does. It goes from 0 to r, because the r is going all the way out to the edge of the circle, and theta goes from 0 to 2 pi because you're going all the way around the circle. Okay, so I'm integrating with respect to r first. Actually, it wouldn't matter here, but this is how it's set up. So I integrate first with respect to r, and I will get r squared over 2, evaluate it at its limits, and I will get the radius of the circle squared divided by 2. Then I have to integrate d theta from 0 to 2 pi, and of course that integral is just 2 pi, and I end up with pi r squared, which is the radius, is the area of the circle. If you didn't put this Jacobian in, you would not get the answer, the correct answer for the area of the circle. In the homework, I asked you to show the geometric interpretation of this new area, this r dr d theta. And here's what it is. If you have a little region and it's a rectangle, what's the area of the rectangle? This is x and this is y. This would be dx, and this would be dy, and the area would be dx dy. Okay, now let's look in polar coordinates. Here you have the variables r and theta. So if and it wouldn't be a rectangle, it'd be a little arc of a circle. R is moving from here to here, and that distance is dr. Right? Now, as theta changes, theta is going to be sweeping out this arc of a circle here. And what is this length? It's not just d theta, it's an arc length of a circle, it's r d theta. So the area is dr times r d theta. you need this arc length here, not just d theta, but this arc length. And this, of course, the size of this will depend on how big r is, and that's why r appears in this equation. So it's dr times r d theta. And you rearrange it to get r dr d theta. But really the r belongs to the d theta. I'm going to erase the screen. Okay, so you can see it just as it is. It's also in the notes. And also there's pictures similar to this that appear in Thomas and in Stewart. So this is a geometric interpretation of polar coordinates. This length is dr. This length is really an arc length, very poorly drawn, is r d theta. Now let's go to cylindrical coordinates. So this would be a triple integral in cylindrical coordinates. So here's the change of variables. X equals r cosine theta, y equals r sine theta, and z equals z. Now we need to compute the Jacobian, so that will be the matrix of partial derivatives. The first terms you already have because those are x and y with respect to r and theta. But z doesn't change with r, so you get a 0 here. Z doesn't change with theta, you get a 0 here, and you get a 1 because dz by dz is equal to 1. And of course z doesn't change with r and theta, so you get the zeros here. Now if you expand along this row, which is the easiest to do, or along this column, depending on whatever you want to use, the bottom line will be that the answer is r cosine squared theta plus r sine squared theta, which is r. In other words, the Jacobian in cylindrical coordinates is the same as the Jacobian in polar coordinates. So here's the triple integral in terms of these variables, x, y, and z, the original variables, Cartesian, and this, of course, that's what we're doing. And now we've transformed it into cylindrical coordinates, r, theta, and z. The function got rewritten, and the dx, dy, dz becomes r, dr, d theta, dz. To show how this works, here's the example of the volume of a cylinder. The cylinder, I just grabbed the wrong thing here. The cylinder has a height h and a radius r, and we want the volume of it. In Cartesian coordinates, the integral would look like this, which is fairly messy. Right, but let's transform to cylindrical coordinates. Remember, the function here is just 1, so there's no change in the function. But we want to change the dx, dy, dz. It's going to have to change into r, dr, d theta. So I'm going to replace dx, dy, dz by dr, r, dr, d theta, dz. And the limits in r are going to be 0 to r because you're going to go all the way to the edge of the cylinder. Edge of cylinder. Something like that. So here's your r. So r varies all the way out to the edge. That's 0 to r. Theta varies all the way around. That's where I get the limit, 0 to 2 pi. And in z, it goes from 0 up to the height of the cylinder, h. So when I integrate the r dr, I get r squared over 2. That's fine. Now I integrate with respect to theta from 0 to 2 pi. I get a 2 pi. And then I integrate with respect to z from 0 to h, and I get pi r squared h, which indeed is the volume of a cylinder of height h and radius r.